All right. In this video, I'm going to cover section 15.5, which is about surface areas. This is going to be a short section, and what we're going to do is to basically give you a sort of like another application of double integral. One of the things you could do is double integrals. And then for that, let's ask this question. Let me start with this question. Given z is equal to f of xy as usual, and suppose you have some region on xy plane. So situation is like this as usual. And then you have some region D. Oops. Let me write this way. Region D on the xy plane. Then now, so this is the surface, z is equal to f of xy. Then now the question is this: find the area of the surface lying above D. So that means if you look, so here's D, and if you look above, and then you will see a portion of this surface. And then the question is to find the area of this part. And let's call this portion S. Let's call this portion S. So this is our S. Okay, then now here's the answer. So the area of this S, which I denote by the way, A of S, meaning area of S, is what? Well, think this way. Suppose you look at a small piece here, small portion, and the area of this is dA, and that's dx dy as usual. Look at this small piece downstairs, small patch, and then look at the corresponding patch above. If you look above, you see the small patch on the surface here. And let's call this ds, small ds. Okay, then basically the area of the surface is obtained by putting them together, namely by adding this small piece over this region D. So that's the first formula for the area of the surface. But of course, this doesn't really give you how to compute the area. So we need to explicitly express everything here in terms of the given data, namely f and xy. So need to express this ds, namely this form you want to differentiate, you want to integrate in terms of the function f dx dy, so that we can compute this double integral. And to do this, let me just magnify those two like this one. If you magnify those, we have a situation like this. So down here, downstairs, we have this rectangle, small rectangle with size dx and dy. That's what we have downstairs. And upstairs, we have this small piece on the surface. So this is our ds. Okay. Then now, if dx and dy are small, we may consider this as a plane. And moreover, we can approximate this as a parallelogram like this one. So this guy here is approximated by a parallelogram. And let's go this side vector A and this vector B. We approximate this. So approximate ds as the parallelogram spanned by A and B. Okay. So then now what's ds then? Well, ds is the area of this parallelogram, and the area of parallelogram spanned by two vectors is computed as the magnitude of the cross product. So ds is now written this way. But what are A and B? Well, actually, A is indeed written as what? So basically, A is a vector where vector is parallel to the vector dx here downstairs. So that means the x component of A is actually dx. And there is no y component because dx is parallel to the x-axis. So there is no y component. And then z component is the increase or rate of change for the z value with respect to x. So that means if you increase your x a little bit, your z value increases by the corresponding derivative with respect to x. And similarly, b is computed as dy, fy, dy. So, therefore, by using those, the cross product is computed as I, j, k dx 0 fx dx and then 0 y fy dy, and then compute the cross product. And if you compute the cross product here, you are supposed to get negative fx dx dy minus fy dx dy and then dx dy. Okay, so therefore, the area ds is the magnitude of A cross B, and the magnitude of A cross B is, take the square of each component and then add them up, squared plus negative fy squared plus dx dy squared square root. And then this is simplified as this. So you can take out the common term dx dy squared out of square root. That becomes dx dy. So this is actually fx squared plus fy squared plus 1 square root and then dx dy. And this is almost ds. This is the approximation of ds. So therefore, the area of the surface the area of S is double integral over d of ds. But what's ds? Well, ds is this. So what you do is just to double integrate fx squared plus fy squared plus square root dx dy. Or, of course, this is the same as partial f partial x squared plus partial f partial y squared. Well, let me just here put 1 in front. It doesn't really matter which one first. And then dx dy over t. So this is the formula for the surface area. And if you didn't really understand the derivation I gave you, it's okay just to know this formula as a formula for the surface area. And indeed, we have seen something like this in calculus 2 actually. For the arc length formula, so let's recall in calculus 2, you guys have seen this x and y. And the y is equal to f of x. A, b. And then the formula for the arc length here, if you remember, is given by the integral from a to b over square root 1 plus df dx squared dx. So that's the arc length formula from calculus 2. And then this is just a direct generalization of this. We have one more variable, we have extra variable y, so we have two terms, and instead of just one integral, we have double integral. So in this sense, the formula we derived for surface area is just a direct generalization of this. Anyhow, so let me just work out one example. Find surface area of z is equal to x squared plus y squared that lies under z is equal to 9. Okay. Can you visualize what's going on? This one, by the way, z is equal to x squared plus y squared. We have seen this already multiple times. This is, so to speak, paraboloid, rotated parabola, with vertex the origin in this case. X, y. Like this. And then, so this is this. This surface is z is equal to x squared plus y squared. And this is called a paraboloid. And then z is equal to 9 somewhere here. It's a cap. Let's say 9 here. So this cap is z is equal to 9. It's a horizontal plane. Then now, the question is find the surface area of this that lies under this. So that means the surface area, this portion, that's below this. Well, how do we do this? Well, let's just apply the formula for the surface area. The area of the surface is the double integral over the region D, 1 plus partial f or partial z partial x squared partial z partial y squared dx dy. That's just a formula, but then now, what's d? Well, but before thinking about what d is, let me just rewrite it. So you can just compute the partial derivative, that's 2x squared and 2y squared. If you just compute the partial derivatives, and they take the square root dx dy. That's fine. Then now what's d? Well, d is basically the shadow of the surface area we are looking at when you light up everything from the above. Okay, that's what this is, right? If you look at this picture here, where is it? This picture here. Basically, d is the shadow of the surface when you light up the surface directly from the above, vertically. So in this case, what's the shadow? Well, in this case, you just project this down on the xy plane. And what you see is this disk. That's our d. Now, what's that? Well, that means that's the same as a disk when z is equal to 9. So this disk is actually equal to 9 is equal to x squared plus y squared. So that's what d is. That means it's a circle. Let me just write it here. So basically, z. Let me just write it more explicitly. Z is equal to x squared plus y squared, and then we are looking at this at elevation. Z is equal to 9, height 9, and that's the same as x squared plus y squared is equal to 9. Well, that means D is pictorially on the xy plane. It's just disk with radius 3. Okay, so what should we do? Well, we want to compute integral like this, where the region of integration is the disk. In that case, what we do is to use the polar coordinates. Remember polar coordinates? X is equal to r cosine theta. Y is equal to r sine theta. And then to use polar coordinates, dx dy becomes r dr d theta. Don't forget this r. And then that's the polar coordinates, but at the same time, indeed here we have 1 plus 4x squared plus y squared here, if you factor out 4. And then often the time, for polar coordinates, you see expression like x squared plus y squared. And for polar coordinates, x squared plus y squared is r squared. So you may actually consider this as part of the polar coordinate formula. Okay, and then in this case, r is from what to what? Well, this is the entire disk with radius 3. So the radius is at most 3, at least 0. So it's between 0 and 3. And the theta is everything, meaning 0 to 2 pi. All right. Then all we have to do is just to plug those into here. And then you get, so therefore, we get double integral d root 1 plus 2x squared plus 2y squared dx dy is, so like I said, this portion is 4 times x squared plus y squared. So this is written as 1 plus 4r squared square root times r dr d theta. And then r is from 0 to 3, and then theta is from 0 to 2 pi. So all I have to do is to compute this integral, compute this double integral. And then for the inner integral, you have to integrate this with r. And for this, to compute the antiderivative of this, you have to use u substitution, u sub, by using u is equal to 1 plus 4r squared. And then, if you work this out, this is your exercise. You are supposed to get pi over 6 37 root 37 minus 1. I'm running out of space. Pi over 6 37 root 37 minus 1. So that's the answer. So that's all I have to say for this section.